So I'm going to ask you to stop the video now and try answering this exercise. You've got here four peaks in this NMR spectrum that correspond to the 4 carbons that you can observe in the 3-butane 2-one. So using a chemical shifts table for carbon-13 chemical shifts, could you identify the peaks in this spectrum? Stop the video now, please. So hopefully you stop the video and have a go at the exercise. So if you think of the table that I mentioned before, hopefully it's clear that the peak at around 200 ppm correspond to carbon-2, the carbonyl group. That's a carbon in a ketone group, and it appears slightly lower than the chemical shift suggested by the table, which is 200 to 220. However, remember that in the case with infrared and in the case of many other spectroscopy techniques, those tables are just an indication of where those peaks are going to appear, but you often find that in the compound itself, because of the environment that carbon is surrounded or that atom is surrounded, they appear in slightly different position, higher or lower than what the table suggests. The other peak that hopefully is easy to identify is the one around 25 ppm, which is typical from a carbon in an alkane group, in this case the methyl carbon-1. Then we have the peaks around 130, 140, these two, that correspond to the 2 carbons involved in the double bond. And looking at it, I would expect that the one that is further away from the carbonyl group, carbon-4, would be this one, the one at lower chemical shift, and the one that is near the carbonyl group, that is more distorted by the by the electronic environment and the environment created by that carbonyl group, is carbon-3. So interpret proton NMR spectra. In a carbon-13 NMR spectrum, the position of the peaks tells us what sort of carbon we have, so we can get structural information from it, but we don't know how many carbons we've got in that particular environment. That is because when we're looking at carbon-13 NMR spectrum, we're only looking at carbon-13, which is 1.3% of all the atoms or the carbon atoms in our sample. When we're looking at proton NMR spectrum, we are looking at all the hydrogens in that compound. So we'll all resonate, they will all show they will all respond to the external magnetic field. So it's going to give us more information. It's going to tell us the position of the peak, it's going to tell us what type of hydrogen, in which environment we have that hydrogen. The area under the peak, the area of those peaks, will tell us the number of hydrogens in that environment. And the splitting of the peaks, and we'll talk about the splitting later, will tell us something about the neighbors of that environment. So not those hydrogens, but the hydrogens in the adjacent carbons. So let's first look at the number of hydrogens. NMR spectrometers, proton NMR spectrometers, draw a line on top of each peak, and we call that integrator trace. And the relative area under those peaks can be measured by measuring the height of that trace. So if you look at this spectrum, this NMR spectrum of a propanoic acid, it has 3 clusters of peaks, and they have different areas. And if we look at the integrator trace, the height of those lines that appear in green in the slide tell us information about how many hydrogens are represented in that particular peak. So if we look at all the heights and we measure them, physically measuring with a ruler, then we can divide, in this case, those three heights by the smallest number, and it tells us the ratio of those peaks. It tells us that these peaks correspond to 1 hydrogen. This peak is double the height, so it will correspond to 2 hydrogens. And this peak here is 3 times the height of the smallest one, corresponds to 3 hydrogens. It could be also double. It could be that this peak, in this case, we don't have enough hydrogens, but if we didn't know anything about the structure of the compound, if we didn't know that it only has 6 hydrogens, this we could also work out that those peak areas 1, 2, 3 could also be 2, 4, and 6. When we know one of the peaks, when we can easily identify one of the peaks as corresponding to a particular hydrogen, then we can attribute the number of hydrogens of that peak to that particular trace height and calculate the others. So I'm going to ask you just very quickly to stop the video now and just identify those 3 peaks, or those 3 clusters of peaks, because as you can see, some of them are more than one peak, and identify to which set of hydrogens those peaks correspond. Stop the video now, please. So in this case, hopefully it was very straightforward, because the ratio of the peak areas is 1, 2, and 3, and it reflects perfectly the structure of propanoic acid, of having 1 hydrogen, 2 hydrogens in this CH2 group, and 3 hydrogens in the CH3 group. So this peak will correspond to the hydrogen of the OH group. This would correspond to the hydrogens of the CH2 group, and the peak around 1 ppm correspond to the hydrogens in the methyl group.